Today, we are not just going to solve problems, we are going to look at a very important topic, photoelectricity. We have photo, then we have electricity. So the diagram on the board displays a sun. That's the sun in the atmosphere there. And we have radiation from the sun rays. And then we have a piece of metal here on Earth's surface. So we see electron, all right, moving away from the surface of the metal. We want to find out why this is so. All right, so there's a packet of radiation from the sun, which is called the photon. Electron here is held on this metallic surface by a form of energy called work function. So when the rays come from the sun, they are focused on the surface of the metal, and then after some times the metal becomes heated, and then because the electrons are very, very mobile, the electrons is exceeded from the surface of the metal, and then you see the electrons possessing kinetic energy and running away from the surface of the metal into the atmosphere. So we want to find the energy that connects these concepts. All right? Albert Einstein did this profound work and was able to suggest energy for this radiation, and then connecting the work function of the metal and the kinetic energy of the electrons. So let us go to the class and see how we can deal with this very interesting topic. Today, the topic we are treating is photoelectricity. And then, just like from our introduction slide, I told us that the sun is somewhere there in the atmosphere, right? Okay, so during the day, the rays from the sun or the radiations are received on the face of the earth. Now, actually, what happens is that when conductors are exposed to this radiation from the sun, the electrons, the mobile electrons on those conductors, especially when the conductors have become heated, the mobile electrons are prone to ejection. All right? And when they are ejected, they possess kinetic energy and they run away from the surface of the metal. So the energy boundaries from the sun, we have the radiation, and the packet of radiation from the sun is energy packet called photon, right? So electrons are usually seated on the face of the metals in a hole which is positively charged. Of course, you know that electrons are negatively charged. Now, when they are situated here, a little disturbance can make them to jump out because they are very, very highly mobile. So that same case that happens here, when the radiation from the sun gets the metal heated, electrons are removed from the surface of the metal, and then they go into an empty space. So here, the energy that keeps the electrons here, that energy is called work function. Work function, represented as mu zero, work function. And then the energy, right? The packet of energy from the sun is energy of radiation, commonly represented as E equals HF. And then this is defined as the Planck's constant times the threshold frequency. F0 means threshold frequency. Okay? So electrons that are going like this, Electrons that are removed or ejected will possess maximum kinetic energy, all right, which is defined as half mv squared, all right, in this case with respect to electron. So when the velocity is maximum, right, these are the different energy cases. So the total energy from here, part of it is used to remove, to overcome this work function, all right, which is energy that keeps the electron inside the hole. And then the rest part of energy of radiation is converted to kinetic energy of the electron. So about Einstein came up, all right, what we call Einstein's equation. Einstein's equation, all right, of photoelectricity. So the first step equation is equal to the energy, the packet of energy from the sun equals work function plus the maximum kinetic energy of the electron. You may call this one as equation 1, all right? The total energy coming, part of it is used to overcome the work function, and the remaining part is possessed by electrons as kinetic energy. So this is the first level equation of Einstein's equations for photoelectricity. So the second function is E is defined as the product of Planck's constant and frequency of radiation. All right, so it will be Planck's constant. We want to bring in frequency, and then this is Planck's constant times threshold frequency, or then we have the formula for kinetic energy is equal to mv squared, of course, maximum velocity. So this involves frequency and then the mass of the electron and velocity of electron. This is the second step equation, all right? And from we know that the velocity of any wave is the wavelength times the frequency of the wave. Of course, if you had treated waves and sound waves, you must have seen a kind of equation like this. So in terms of the speed of light, this velocity now becomes the speed of light and is equal to lambda times f. So if we make f the subject, our f is equal to speed of light divided by lambda. Now, if we want to bring in the wavelength of the radiation, all right, the expression, equation 2 becomes, all right, equation 2 becomes h times c over lambda, all right, and then we have h times c over lambda 0, where lambda 0 is actually the threshold of the wavelength of radiation. So this is going to be plus half. Then we have mv squared, where the velocity is maximum. Okay, we can call this one the third equation. Now, these are the three respective equations of Einstein as regards photoelectricity. Okay, now this phenomenon, photoelectricity, what does it actually mean? Okay, like the name signifies, we have photo, which means light, and then we have electricity. In other words, the electricity generated as a result of some light rays being focused on a conductor. So photoelectricity could also be referred to as photoelectric effects. Okay, so these are the three levels of equations that we have from Einstein. Okay, now C is a constant. Experiment has shown that the value of C is 3.0 times 10 raised to power 8 meters per second. And then the Planck's constant, the value is 6.63 times 10 raised to power minus 34 joules second. So those are the constants in the equations. Of course, they would have provided in brackets when they want you to solve questions. They will provide the values for the constants. All right. Sometimes too, the mass of electron could be given. I think it's 9.1 times 10 raised to power minus 31 kilograms. And then the electron, of course, the velocity of electron is not a constant. So these are the constants that we are likely to be provided when problems are given to be solved in of um, this part of study. All right, the next thing we're going to look up for, we're going to look at is the next thing is stopping potential. All right, commonly represented as V, capital letter Vs. All right, something like the stopping potential. Now, the electrons released during the process of photoelectricity can be brought to a point. All right, so at that point where the electron is expected to be brought to a stopping point or to a rest. All right, in physics, stopping point is referred to as a rest. All right, so the when it is moving, it possesses kinetic energy or maximum kinetic energy, and when it's going to rest, then we expect that work should be done against it, which is electrical work. So the electrical work is defined as electron times, or the charge times the potential difference. So the point where electron is brought to rest, the point where E is brought to rest, the kinetic energy, all right, the maximum kinetic energy of electron is equal to work done, all right, is equal to work done. So our V here, the potential difference here is what we call the stopping potential. And if we make Vs the subject, what we are going to have becomes, of course, bring in the value of kinetic energy, we have half mv squared is equal to Q times the stopping potential. Therefore, stopping potential Vs is equal to mv squared divided by 2 times Q. This expression is expression for stopping potential. Should they ask you to calculate the stopping potential, you know that the stopping potential as applied to photoelectricity is mass of electron times the maximum velocity of electron divided by 2 times the electronic charge. I hope you're learning something. All right. Here there's a problem from the topic we just treated, that is photoelectricity. Some of the applications will come in the form of what is here as a question for us to solve. Calculate the frequency of photon whose energy is required to eject a surface electron with a kinetic energy of 1.97 times 10 raised to the power minus 19 electron volts if the work function is, they give us this work function, right? And then in the bracket, we are told that 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joules. And then Planck's constant is given as H equals 6.6 times 10 raised to the power minus 34 joules second. Now we need to work on this right away. How do we do that? So the work function is said to be this, right? And then we are provided the solution. Okay, they told us that for every 1 electron volts, we have 1.6 times 10 raised to the power minus 19 joules. All right, and they told us that the Planck's constant, I told you before, 6.63, but this time they said 6.6, just 6.6 times 10 raised to the power. All right, 6.6 times 10 raised to the power minus 34 joules second. Okay, and some other parameters from the question, they told us that the kinetic energy, all right, maximum kinetic energy was given to be 1.97 times 10 raised to the power minus 19 electron volts. And we're also told that the work function given as um, given as 1.33 times 10 raised to power minus 19 electron volts. So it is the frequency of radiation or frequency of photon that they want us to find. I mean, if you got all of this information, there is nothing here that you will not be able to work out. So we come to this part of the board, and then we know that the first level equation, you can remember the first level equation, you can remember the second level equation. Since it concerns frequency, of course, they may be referring to existence of the first level and second level equations, all right? So what we are going to do from the first level, we said E equals work function plus maximum kinetic energy, all right? Work function given, maximum kinetic energy is given. So we try to get that first. So we're told that the work function is 1.33 times 10 raised to power minus 19 electron volts. So we're going to add it to kinetic energy of 1.97 times 10 raised to power minus 19 electron volts. So if we do that, we are going to have 2.1. If you add that, you have 2.1 times 10 raised to power minus 19 electron volt being equal to the frequency of radiation, all right? But we know that the frequency of radiation has relationship with the frequency, the energy of radiation has a direct relationship with frequency of radiation. Can you remember that? All right, so we know that BERT, all right, our energy of radiation is Planck's constant times frequency. Okay, so if we do that, we're going to have frequency of radiation, which is what they want us to find, becomes energy of radiation divided by the Planck's constant. Here we have the energy of radiation. So, but the energy of radiation is in electron volts, right? So it cannot combine with Planck's constant that is already expressed in its SI unit, joules second. So we need to convert energy of radiation to joules, which is the reason why they give us 1 electron volt is equal to 1.6 times 10 raised to power minus 19 joules. So the energy we calculated was 2.1 times 10 raised to power minus 19 electron volts. So converting it to joules, what we will have would be 2.1 times 10 raised to power minus 19 times 1.6 times 10 raised to power minus 19, now in joules, all right? That was possible because, all right, since our 1 electron volt is equal to 1.6 times 10 raised to power minus 19 joules. So if you want to convert this to joules, just multiply through by that value of 1.6 times 10 raised to power minus 19 joules, right? It's becoming a little bit more interesting. So we know that our E is equal to H of F. So our H of F, therefore, is equal to E over H. The result is equal to, I have 2.1 times 10 raised to times 1.6 times 10 raised to power minus 38, all right, all divided by Planck's constant is 6.6 times 10 raised to power minus 34. This value is per second, all right, which is the same thing as hertz, all right. Per second means hertz. So if we evaluate this, our frequency is going to be 2.2 times 10 raised to power 2.1 times 1.6 times 10 raised to power. Use standard form, take this one up, and then you're left, you're going to be left with minus 4. All right. So here, This is dividing 6.6. So the result is going to be 3.36 times 10 raised to power minus 4 divided by 6.6. So if we divide this divided by 6.6, and the result is going to be 5.09 times 10 raised to power minus 5 hertz. So from the information we are given, this therefore stands as the value of the frequency. I hope you learned something. This is very interesting. So you look forward to many more questions of this nature. Okay? And I want you to go back, sit down, and look at what has been done to make sure you learn it and let it form part of your IQ. Thank you.